A mining company in Australia recently had two bulldozers break down on the same day. The first was a 2023 model worth over $2 million. It threw an error code, shut down completely, and sat idle for 3 days waiting for a technician to fly in with a laptop to diagnose and reset the system. The second was a 1985 Caterpillar D9L. The operator heard a strange noise, shut it down, crawled underneath with a wrench, tightened a loose bolt, and was back to work in 20 minutes. That's the difference between a bulldozer that needs a laptop and one that doesn't. The 1980s was the last decade before computers invaded the cab, before emission systems required diagnostic software, before a simple repair meant plugging in and downloading updates. These 10 machines represent the pinnacle of pure mechanical engineering, when a skilled operator and a good toolbox were all you needed to keep a bulldozer running. And right now, contractors are paying premium prices to get their hands on these laptopless legends. Number 10. John Deere 850C. Let's start with a machine that doesn't get enough recognition in the heavy equipment world. The John Deere 850C crawler dozer, introduced in the mid-1980s, represented Deere's serious commitment to competing in the large dozer market. This wasn't some farm tractor with a blade bolted on. This was a legitimate heavy construction machine weighing around 57,000 pounds with approximately 200 horsepower. What made the 850C special was John Deere's agricultural equipment DNA translated into construction equipment. Deere had spent decades building tractors and machinery that farmers could maintain themselves in remote locations without dealer support. That same philosophy permeated the 850C's design. Every system was straightforward, logical, and accessible. Hydraulic components were positioned where you could actually reach them. Filters and service points were clearly marked and easy to access. The engine in the 850C was a turbocharged John Deere diesel that embodied simplicity and reliability. No computer-controlled fuel injection, no sensors monitoring every parameter, no electronic governance of engine speed, just a mechanical fuel pump, a turbocharger, and proven internal components that operators understood intuitively. When something went wrong, you could hear it, feel it, or see it. Diagnosis happened through experience and observation, not diagnostic codes and software. Operators loved the 850C for its honest, predictable behavior. The controls were direct mechanical and hydraulic linkages that provided immediate feedback. When you moved the blade control lever, you felt the hydraulic pressure building, heard the pump loading, and saw the blade respond. This direct connection meant skilled operators could work with incredible precision, feeling their way through material and adjusting based on machine feedback rather than electronic displays. The 850C's undercarriage was built to John Deere's agricultural equipment standards, which meant serious over-engineering for durability. Track components routinely exceeded their rated service life, and the oscillating track frames absorbed shock loads without transmitting stress to the mainframe. Even today, 40-year-old 850Cs show remarkably little structural wear, testament to thoughtful mechanical design that didn't rely on electronic monitoring systems to prevent abuse. Number 9. Fiat-Allis FD30B. The Fiat-Allis FD30B represents an interesting chapter in heavy equipment history. Fiat-Allis was the result of Italian manufacturer Fiat acquiring Allis-Chalmers's construction equipment division, and the FD30B showed the best of both companies' engineering philosophies. This large crawler dozer, weighing approximately 85,000 pounds with around 335 horsepower, competed directly with Caterpillar's D8 series. What made the FD30B distinctly laptopless was its commitment to proven mechanical systems over innovation for innovation's sake. Fiat-Allis engineers weren't trying to reinvent bulldozers, they were trying to build the most reliable, maintainable machine possible. The result was a dozer that used well-established component designs, conventional powertrains, and straightforward hydraulic systems that any competent mechanic could understand and repair. The FD30B's control system was entirely mechanical and hydraulic. Every lever, every pedal, every switch directly activated a mechanical or hydraulic component. There were no electronic intermediaries, no computer modules interpreting your inputs and deciding how the machine should respond. This direct control gave operators an intimate connection with the machine. You learned to read subtle feedback through the controls, understanding soil conditions, blade loading, and engine performance through feel and sound. The engine was a naturally aspirated or turbocharged diesel depending on configuration, but either way, it was fundamentally mechanical. A mechanical fuel pump delivered diesel at pressures determined by engine speed and load. No computer-adjusted injection timing or fuel delivery based on sensor inputs. The engine ran at the speed you set with the throttle, delivering power in a predictable linear way that operators could anticipate and work with. What contractors particularly appreciated about the FD30B was its serviceability in remote locations. Mining operations in Africa, South America, and other regions with limited infrastructure found these machines ideal because they didn't require specialized diagnostic equipment or factory-trained technicians. A skilled mechanic with basic tools could maintain and repair virtually any system on the dozer. This independence from dealer support networks made the FD30B particularly valuable in developing regions. Number 8. Dresser TD40E. Dresser Industries, which eventually acquired International Harvesters Construction Equipment Division, produced the TD40E as their flagship large crawler dozer. This machine, weighing approximately 110,000 pounds with around 425 horsepower, represented Dresser's vision of what a heavy construction dozer should be: powerful, durable, and refreshingly uncomplicated by electronic systems. The TD40E featured a massive Cummins diesel engine that was entirely mechanical in operation. Cummins had perfected mechanical fuel injection systems that delivered impressive power and efficiency without requiring computer control. The engine in the TD40E responded instantly to throttle inputs, delivered power smoothly across its operating range, and could be adjusted and tuned by mechanics using nothing more sophisticated than screwdrivers and wrenches. The transmission and final drives used gear-driven mechanical systems that were proven reliable and field serviceable. Power shift transmissions operated through hydraulic clutch packs, but the control logic was entirely mechanical. Valves, springs, and mechanical linkages determined shift points based on load and speed. No computer needed to calculate optimal shift timing. The system's mechanical design inherently provided appropriate shift characteristics. Operators remember the TD40E for its raw, unfiltered power delivery. Modern bulldozers use computer-controlled transmissions to smooth out power application, preventing wheel slip and optimizing efficiency. The TD40E had no such systems. Power went from the engine through the transmission to the ground with minimal intervention. This meant skilled operators needed to modulate the throttle and manage the machine actively, but it also meant you had complete control over how power was applied. The hydraulic system on the TD40E epitomized 1980s bulldozer simplicity. Gear pumps driven directly off the engine delivered hydraulic pressure to control valves. The valves were entirely mechanical, with spools that moved in response to lever position, directing fluid to hydraulic cylinders. No proportional electronic controls, no pressure sensors, no computer managing system parameters, just hydraulic fluid moving through steel lines in response to mechanical valve positions. Number 7. Komatsu D355A-3. Komatsu's D355A-3 dozer from the 1980s represented Japanese heavy equipment engineering at its finest. This large crawler, weighing approximately 130,000 pounds with around 410 horsepower, competed directly with Caterpillar's D9 and proved that Komatsu could build world-class heavy equipment without relying on electronic systems. The D355A-3 featured Komatsu's own turbocharged diesel engine that exemplified mechanical reliability. Komatsu engineers had a reputation for conservative, proven designs rather than pushing technological boundaries. The engine used a mechanical fuel injection pump, mechanical governors to control maximum speed, and entirely conventional valve trains and cooling systems. Everything about the power plant could be understood, maintained, and repaired with mechanical knowledge and basic tools. What set the D355A-3 apart was Komatsu's attention to the operator-machine interface. The cab design provided excellent visibility, and the control layout was intuitive and ergonomic. But more importantly, the controls themselves provided superb feedback. Lever efforts were carefully calibrated to give the operator tactile information about system loading and machine status. You could feel through the steering levers when the machine was approaching its traction limits. You could sense through the blade control when you were loading the bowl optimally. The undercarriage design on the D355A-3 showed Komatsu's engineering excellence. Track frames, rollers, and drive systems were engineered with generous safety factors and high-quality materials. But they achieved durability through good mechanical design rather than electronic monitoring systems. There were no sensors warning operators about component wear or improper loading. Instead, the systems were simply built strong enough to withstand abuse while providing long service life. Contractors who operated D355A-3s in remote locations particularly valued their independence from electronic support. Mining operations in Mongolia, construction projects in remote parts of Canada, land clearing in the Amazon, these machines worked far from dealer networks and technical support. When problems arose, they were mechanical problems that could be solved mechanically. No laptops, no diagnostic software, no calls to technical support hotlines, just skilled mechanics applying knowledge and experience to keep the machines running. Number 6. Caterpillar D8L. The Caterpillar D8L represents peak 1980s bulldozer engineering from the industry leader. Introduced in 1983, the D8L was Caterpillar's workhorse large dozer, weighing approximately 90,000 pounds with 335 horsepower. This machine embodied everything Caterpillar had learned over 5 decades of building crawler tractors, refined into a package that needed nothing but diesel fuel and periodic maintenance. The D8L's mechanical drivetrain was the product of continuous evolution. Caterpillar had been building D8s since the 1930s, and by the 1980s they had optimized every component for reliability and performance. The power-shift transmission used hydraulically actuated clutch packs, but shift control was entirely mechanical. A clever arrangement of valves, springs, and mechanical linkages provided smooth, precise shifts based on load and operator input, no computer required. What made the D8L particularly laptopless was its diagnostic simplicity. When something went wrong, the machine told you through changes in behavior, sound, or visible issues. Experienced operators and mechanics could diagnose problems through observation and systematic troubleshooting. Loss of power pointed to fuel system or turbocharger issues. Unusual noises indicated bearing problems or loose components. Sluggish hydraulics suggested pump wear or contaminated fluid. Every problem had mechanical causes and mechanical solutions. The D8L's engine was a turbocharged Caterpillar diesel that exemplified proven technology. Mechanical fuel injection delivered precise fuel metering across all operating conditions. The turbocharger was a simple fixed geometry unit that provided boost pressure without requiring electronic wastegate control. Cooling systems used thermostatic valves and mechanical fans. Everything was straightforward, logical, and repairable in the field. Operators loved the D8L for its predictable, consistent behavior. The machine responded the same way every time to the same inputs. There were no adaptive systems learning your operating style, no computer adjusting parameters based on conditions. The D8L was a tool that worked exactly as designed, allowing skilled operators to develop intimate familiarity with its characteristics and capabilities. This consistency meant experienced D8L operators could maximize productivity through refined technique rather than relying on electronic aids. Number 5. International Harvester Dresser TD25G. The International Harvester TD25G, which later became the Dresser TD25G after corporate reorganization, was a large crawler dozer that competed in the 75,000-pound class. This machine represented International Harvester's final generation of large dozers before their construction equipment division was sold, and it showed the culmination of their engineering philosophy. The TD25G featured an international diesel engine or optional Cummins power plant, both entirely mechanical. International's own engines had agricultural equipment heritage, designed to run continuously under high loads in remote locations. The mechanical fuel injection systems were robust and relatively simple, allowing field adjustments and repairs without specialized equipment. Governors and throttle controls were mechanical assemblies that operators could adjust and tune with basic hand tools. What made the TD25G distinctly laptopless was its utilitarian design philosophy. Every component served a clear purpose, and unnecessary complexity was eliminated. The hydraulic system used gear pumps and simple directional control valves. The steering system employed mechanical clutches and brakes, controlled directly by hand levers with no hydraulic or electronic assistance. The transmission was a power shift design with mechanical shift control logic. Operators appreciated the TD25G's honest, straightforward operation. The machine demanded active engagement and skill from its operator. You couldn't just set controls and let automation take over because there was no automation. Maintaining optimal productivity required constant attention to blade angle, cutting depth, ground speed, and engine loading. This active operation style created skilled operators who truly understood earth-moving principles rather than just following electronic guidance. The TD25G's serviceability was exceptional. International Harvester designed their equipment to be maintained by farmers and contractors with basic facilities, not just by factory-trained technicians with specialized tools. Access panels were logically placed, components were arranged to allow removal and installation, and the service manual provided clear mechanical procedures for every maintenance task. No diagnostic flowcharts requiring electronic test equipment, just straightforward mechanical troubleshooting. Number 4. Komatsu D85E-21. The Komatsu D85E-21 was a medium-large crawler dozer that found enormous success in the 1980s. Weighing approximately 45,000 pounds with around 200 horsepower, this machine occupied the sweet spot between the compact dozers used for lighter work and the heavy dozers needed for major earth moving. The D85E-21 could handle serious production work while remaining manageable and economical to operate. Komatsu engineered the D85E-21 with characteristic Japanese attention to mechanical refinement. The engine was a turbocharged Komatsu diesel that delivered smooth, reliable power through entirely mechanical systems. Fuel injection was mechanically timed and metered. The turbocharger used fixed geometry and wastegate controlled by mechanical linkages responding to intake pressure. Everything about the power plant was conventional, proven, and fundamentally simple. The hydraulic system on the D85E-21 demonstrated Komatsu's understanding of what operators actually needed. Tandem gear pumps provided hydraulic flow for implement control and steering functions. Control valves were mechanically operated through direct linkages from the control levers. The system provided excellent control precision and feedback without requiring electronic proportional valves or computer management. What made the D85E-21 particularly successful was its balance of capability and accessibility. The machine was large enough to handle substantial work, but simple enough that small contractors could own and maintain it without requiring extensive support infrastructure. This democratization of heavy equipment capability meant smaller companies could compete for projects that previously required larger contractors with more resources. The D85E-21's undercarriage design reflected Komatsu's commitment to durability through good mechanical engineering. Track systems used sealed and lubricated components that required minimal maintenance while providing excellent service life. The oscillating track frames absorbed shock and distributed loads effectively without needing electronic monitoring or active suspension systems. Everything worked through careful mechanical design and quality manufacturing. Number 3. Caterpillar D9L. The Caterpillar D9L deserves special recognition as perhaps the ultimate laptopless bulldozer. Introduced in 1986, the D9L represented the final evolution of the mechanical D9 before electronic systems began appearing in later models. Weighing approximately 107,000 pounds with 410 horsepower, this machine was large, powerful, and entirely mechanical. The D9L's engine was a turbocharged Caterpillar 3408 diesel that epitomized 1980s power plant design. Mechanical fuel injection delivered precise metering across all conditions. The turbocharger was a fixed geometry design that provided boost without electronic controls. The engine management system consisted of a mechanical governor, mechanical fuel pump, and mechanical throttle linkage. Everything worked through springs, levers, gears, and hydraulic pressure. Nothing more sophisticated required. What made the D9L legendary was its combination of power and reliability without electronic complexity. The machine delivered serious production capability while remaining fundamentally simple. Operators could understand every system, mechanics could diagnose and repair problems without diagnostic computers, and the dozer kept working in environments where electronic systems would fail. The D9L's transmission and final drives represented decades of Caterpillar engineering refinement. The power shift transmission used hydraulically actuated clutches, but shift control was entirely mechanical. A sophisticated arrangement of valves, accumulators, and mechanical linkages provided smooth, progressive shifts that matched engine power to ground speed optimally. The system worked so well that electronic controls couldn't significantly improve it. Military forces around the world particularly favored D9Ls for their mechanical simplicity and battlefield durability. The Israeli Defense Forces, for example, operate heavily armored D9L variants for combat engineering. These machines work in extremely harsh conditions, often far from technical support, frequently under combat stress. The D9L's mechanical systems continue functioning when electronic systems would fail, making them irreplaceable for certain applications. The D9L community today is remarkably strong. Owners maintain these machines meticulously, rebuild them completely when necessary, and refuse to replace them with newer equipment. The mechanical simplicity, proven reliability, and superior power delivery of the D9L continue to make it the preferred choice for contractors who value productivity over electronic features. Number 2. Caterpillar D8H. Late mechanical models. Before the D8L refined the formula, and long before electronics ever touched the cab, there was the Caterpillar D8H, one of the most brutally simple, mechanically honest bulldozers ever put into service. Produced through the 1970s and into the early 1980s in its late mechanical variants, the D8H represents the purest expression of Caterpillar's old-school engineering philosophy. Build it heavy, build it simple, and assume it will be abused every single day of its life. The D8H wasn't designed to be efficient. It wasn't designed to be comfortable. It was designed to work continuously, predictably, and without excuses. At roughly 85,000 pounds, and powered by Caterpillar's legendary mechanically injected diesel engine, the D8H delivered power the old-fashioned way. No electronic fuel controls, no sensors, no engine management system deciding how much power you were allowed to use. The throttle cable moved a mechanical governor. The governor controlled fuel delivery. More throttle meant more fuel, less throttle meant less fuel. That was the entire logic chain, and it never needed a software update. Operators trusted the D8H because it behaved exactly the same every single day. Cold mornings, hot afternoons, high altitude, poor fuel quality, it didn't matter. The engine told you what it was doing through sound and vibration. If it lugged, you backed off. If it screamed, you eased up. You didn't wait for a warning light or an error code because none existed. The transmission was equally straightforward. The power shift system relied on hydraulically actuated clutch packs, but the control logic was entirely mechanical. Valves, springs, and hydraulic pressure determined engagement. Nothing digital, nothing electronic. When a gear engaged, you felt it. When a clutch started to slip, you heard it long before it became a failure. That sensory feedback is exactly what modern machines have lost. One of the reasons the D8H still appears in mining, forestry, and land clearing footage today is its legendary tolerance for neglect. These machines ran in places where oil changes were late, filters were dirty, and maintenance schedules were more of a suggestion than a rule. And yet they kept going. When something finally failed, it failed mechanically, and mechanical failures can be fixed anywhere. Need to adjust fuel delivery? A wrench. Need to diagnose power loss? Check air, fuel, exhaust. Need to keep working until parts arrive? You could often limp it along without risking catastrophic damage. That's why D8Hs became favorites in remote operations across Australia, Africa, and South America. Exactly the places where modern machines struggle the most. No laptops, no dealer technicians, no diagnostic ports, just steel, hydraulics, and experience. Even the operator station reflected this mindset. Visibility was excellent. Controls were heavy but precise. There was no insulation from the machine's behavior, and that was intentional. You were meant to feel the load, hear the engine strain, and respond accordingly. Skilled operators could push a D8H harder than any computer ever would, because they knew when to stop. Today, the D8H occupies a rare position in the used equipment market. It's old enough to be entirely mechanical, but common enough that footage, parts, machines, and rebuild knowledge still exist. Contractors who buy one aren't buying nostalgia, they're buying uptime. They're buying a bulldozer that doesn't care about software, emission sensors, or electrical gremlins. In many ways, the D8H is the last warning sign before the industry changed forever. After it came refinement, then electronics, then dependence. The D8H belongs to the final generation where a bulldozer answered to the operator alone, and that's exactly why it still earns its place near the top of this list. Number 1. Caterpillar D10. At the top of our list sits the Caterpillar D10, the ultimate laptopless super heavy bulldozer. Introduced in 1977 and continuing through the 1980s in its original mechanical form, the D10 represented the pinnacle of what could be achieved through pure mechanical engineering. Weighing approximately 180,000 pounds with 700 horsepower, this machine moved Earth on a scale that still impresses today. The D10's engine was a massive turbocharged Caterpillar diesel that delivered incredible power without requiring electronic management. Mechanical fuel injection provided precise metering, mechanical governors controlled maximum speed, and the entire engine management system operated through proven mechanical components. The engine responded instantly to throttle inputs, delivered power smoothly across its operating range, and could run continuously under maximum load indefinitely. What made the D10 the ultimate laptopless bulldozer was the scale at which mechanical engineering was executed. Every system had to work flawlessly under enormous loads and stresses, yet everything remained mechanical and field serviceable. The power shift transmission managed clutch packs capable of handling 700 horsepower through mechanical valve bodies and hydraulic controls. The final drives transferred that power to the ground through massive gears and bearings, all operating without electronic monitoring. The D10's hydraulic system demonstrated what could be achieved with conventional technology when properly engineered. Multiple gear pumps provided hydraulic flow for the blade, ripper, and steering systems. Control valves were massive mechanical assemblies that operators manipulated directly through control levers. The system delivered precise control and incredible force without requiring proportional electronic valves or computer management. Operators who ran D10s described them with genuine reverence. The machine provided unfiltered feedback about every aspect of its operation. You felt the ground through the seat, heard engine loading through changes in turbo whistle and exhaust note, and sensed hydraulic system status through control lever effort. This complete sensory feedback allowed skilled operators to maximize productivity while protecting the machine from damage. The D10 proved that mechanical systems could deliver world-class performance when executed properly. Modern D11 bulldozers are larger and more powerful, but they require laptops for diagnostics, electronic controls for operation, and computer systems to manage emissions and performance. The D10 needed none of that. It needed diesel fuel, engine oil, hydraulic fluid, and a skilled operator. Everything else was just metal, gears, and hydraulic pressure working in harmony. Mining companies that own D10s face the same question operators of other machines on this list confront. Why keep running 40-year-old equipment when newer alternatives exist? The answer is always the same, because the D10 still works, still produces, and still delivers value. The mechanical systems that made it laptopless in 1980 are the same systems that keep it running in 2025, maintained by mechanics who understand machines rather than software engineers who understand code. These 10 bulldozers from the 1980s prove that laptop-free operation wasn't a limitation, it was a feature. The Caterpillar D10's pure mechanical power, the Komatsu D355A-3's refined simplicity, the Dresser TD40E's field serviceability, all these machines succeeded precisely because they didn't need computers. Modern bulldozers offer undeniable advantages. They're more fuel efficient, they meet emissions regulations, they provide operator assistance features that improve safety and productivity, but they've sacrificed independence, simplicity, and field serviceability. When something goes wrong with a modern bulldozer, you're calling for technical support and waiting for someone with a laptop. When something goes wrong with a 1980s bulldozer, you're grabbing your toolbox and fixing it. The laptopless era represents the peak of mechanical engineering in heavy equipment. Engineers had refined designs over decades, optimizing every component for reliability and performance without being able to rely on computers to compensate for weaknesses. The result was machinery that worked through elegant mechanical solutions rather than electronic band-aids. These machines taught generations of operators to truly understand earth moving. Without GPS guidance, you learned to grade by eye and feel. Without electronic engine management, you learned to listen to the engine and adjust your technique. Without automated transmission controls, you learned to manage power delivery manually. These skills created craftspeople who understood their trade at a fundamental level. The 1980s bulldozers still running today aren't museum pieces or nostalgic relics. They're productive machines earning money for their owners, often outperforming newer equipment in reliability and uptime. They prove that good mechanical engineering doesn't become obsolete just because something newer exists. And they remind us that sometimes the best diagnostic tool isn't a laptop plugged into a computer port. It's a skilled mechanic with a good ear and 30 years of experience.